just to make sure that you guys know which class you are in, this is the P4 science class, and my name is Teacher Bobby. Okay, so let's start. So today we'll be focusing on the 3 states of method. Okay, today we'll be focusing on the 3 states of method. And then we'll also take a look at solid and liquid. Okay, so those will be focusing on the 3 states, but sorry, we'll be looking at the 3 states, but focusing only on 2. Okay, solid and liquid. So there are 3 states. They are solid, liquid, and gas. You have to take note that for metal, all of them have mass and occupy space. So if it's something that does not have mass or occupy space, they will be considered as a non-metal. Okay. Now, what is volume? So volume is something that it is space that an object occupies. Okay, it is the amount of space an object occupies. So it is not the volume of your computer, it's not the volume of the TV, but the volume of the object, the space that it takes up. Okay, so generally we will use a balance, okay, some form of balance to measure mass. Okay, although there are also other balance that are used to measure weight, but most of the time we use things like a scale. Most of the time we use things like a scale for weight. Okay. So from here, some of you, my guys, might have already seen this if you have came from the earlier lessons. Okay. So does the shape or does the size of the object determine the mass? Okay. So for those who haven't seen this, how many of you, what do you think? Is it a yes or no? Does the size of the object determine the mass? So let's take a look at this little experiment that is recorded. And maybe you guys can guess who is the one doing the experiment. Whose hand do you think this is? A lot of people are saying it's me. I don't know what's your clue. How do you know it's me? There are people who say it's Mr. Diaz. There's also people who say it's Mr. Arif. Okay, so this is based on the primary science team. So there's only that many people in the primary science team. Okay, so based on this, let's watch the last part. Okay, we can tell that the cup, okay, the cup is definitely bigger than the glass bottle. This is smaller. Okay, so if that's the case, right, which object has a bigger mass? There's no sound. Okay, which object has a bigger mass? So as you all should know or know by now, the answer is the glass bottle. But how did you know it is the glass bottle? Because you're watching a video. So you yourself is not physically holding on to the object. There are also heavy plastics. So how do you know? Okay, based on the video. So based on the video, how do we know that the glass is heavier? So look at this. This is not a weighing scale. This is a balance. This is actually a beam balance. So based on the beam balance, you will notice that here, the side with the glass bottle went down. Okay, the side with the glass bottle went down. So when we are using a balance, right? If the side that goes down will have a greater mass. Okay, the side that goes down will have a greater mass. So in this case, since it went down on the right side, since it went down on the right side, that means the glass bottle has a greater mass. And that is our conclusion. We can conclude that So with that, we can conclude the object with a bigger mass does not always occupy more space. Okay, because if it's bigger, then you occupy more space. But this one is actually the smaller glass bottle that is having a bigger mass. Okay, you will actually learn more about this in secondary school as well, density. So some of you guys might have heard this term before, but you will learn more about it in secondary school. Okay, so hopefully the video was clear enough, or if you were able to understand what I said. Let's go to the next slide. So does matter occupy space? Okay, so if we think about matter, right? When we talk about matter, we'll be thinking of the three states: solid, liquid, and gas. Okay, solid, liquid, and gas. So for solid and liquid, it is very obvious, okay, because we can touch it, like the Apple Pencil. I touch it, I know it occupies space. Like the water in the bottle, it is definitely occupying space, because if I want to put in more water, it will spill out. If I put in anything inside the bottle, let's say an ice cube, the ice cube will also push the water out. But what about gas? How do we know gas occupies space? So since we can't really catch gas, can you? Can you catch gas? I'm trying to catch the gas in front of me, but I don't think I'm being very successful. Okay, I don't think I'm successful in catching gas. Okay, if you guys can catch gas with your hands, I'll be very, very surprised. Okay, but if you do, good job for you. Okay, so how can we conduct an experiment? Okay, how can we conduct an experiment to show that gas occupies space? Okay, to show that gas occupies space. So we'll be doing the 4 steps. Okay, we'll be doing the 4 steps. We will be, okay, fill a clear fish tank with water. And someone mentioned there's a typo here. There's a missing O. Okay, we will have a clear fish tank. Basically, you can see through the fish tank. We add it with water. Okay, in this case, the water is colored water, so it'll be more obvious. Okay, we'll mark where the water starts. Okay, and then we'll put a balloon inside the fish tank. Okay, we'll put a balloon inside the tub of water or the tank of water. Then we'll pump air into the balloon. Okay, so how will it look like? It will look like this. So does air occupy space? So it will look something like this. Okay, once this title screen is gone. So as you can see, the water and the balloon are already in the tank. So our friendly hand over there labeled on the tank the original water level. Okay, and then she starts to pump the air in. Okay, this one is a female teacher. Okay, it's not me, I'm male. Okay, so for this one, it's a female teacher. It's a female hand. Let's see if you guys can guess this, whose hand this belongs to. It belongs to a she. Okay, so you'll notice that the original water level is here, but the new water level is a lot higher now. Okay, my finger is pointing at the wrong place. There. Okay, the new water level is now a lot higher. Okay, so this means that, what does this mean? Okay, if there's an increase in water level, what does it mean? Okay, what caused the water level to rise? Why does it look like a pen? Okay, so what caused the new water level to rise? If you notice, right, the video did one more step, okay, that is not stated in the instruction, and it should be done. Okay, mark the new water level. Okay, you need to mark the new water level so you know what you are comparing. So remember to mark the new water level so you can just directly compare on the tank. Okay, so if that's the case, what caused the water level to rise? So some of you guys were nice enough to have already mentioned the answer in the chat instead of saying emotional damage. That was pretty nice of you. Okay, so yes, it is the air in the balloon. Okay, is air in the balloon. Okay, so the air in the balloon, right? Or air entered the balloon. Okay, and then my head want to be on my hand instead of my head. Okay, air entered the balloon. It occupied space. Okay, it occupied space in the balloon, and it pushed the water away. Okay, and it pushed the water away. So because of that, this shows that it has volume. So this shows that air in the balloon occupies space and have volume. Okay, so what does this allow us to conclude from this experiment? Okay, what are we able to know from this? Air occupies space and has volume. Okay, so from here, we can conclude that solid and air occupies space and have mass. Okay, so let us try to match the different states. Okay, so this slide, it's very familiar. It's like the slide from last week. So what do we know about the chair? The chair is a, okay, so someone said the chair is a solid. Yes, suddenly all the solid rush in. Okay, so then what about the balloon? Okay, once again, all the names rushed in. Okay, the balloon is gas. So that means the orange juice has to be liquid. So for this, for those who are confused, we're talking about air in the balloon. Okay, not the balloon itself. The balloon itself is solid. Okay, and this one, we're talking about orange juice. Or some people who are on the lazier side might just shortcut and just say OJ. Okay, okay. So from here, we know there are 3 states of matter, and they are solid, liquid, and gas. Okay, generally we say in this order, but it is not wrong for you to say that, oh, they are liquid, gas, and solid, or gas, solid, liquid. Okay, it is fine to rearrange the 3 states as long as you mention all 3. But being a habit, I've been saying solid, liquid, gas. Okay, I'm pretty sure your teacher tend to say it in that order as well. Is gaseous state the same as gas state? Yes. Okay, some people will say gas, some people will say gaseous. They are technically the same, just that it's different form. Okay, one is an adjective, one can be a noun. Okay, gas is a noun, gaseous an adjective. So, can an object exist in all 3 states? Okay, can an object exist in all 3 states? Basically, can this one thing exist as solid, liquid, and gas? Okay, and the answer is actually yes. It's already shown on screen actually. Yes. Okay, so water, the source of our life. Okay, if we don't drink water, we will pass away. Okay, we will not live for long. Okay, can exist in all 3 states. Okay, so basically it exists in the liquid state. It exists in the air in the form of water vapor, which you will actually learn in the future. And it also exists in the form of ice. It can be ice cubes, snow, okay, glaciers, this kind of ice. So many of you are asking, what about plasma? Plasma is metal, okay, but it's not in the primary school syllabus. It's actually not really in any syllabus for now. So we'll only be focusing on the 3 states that have been researched extensively. Okay, plasma has not been that well researched yet, but it is considered as another state. Okay, but for primary school, we are only focusing on 3 different states. Okay, even if you want me to explain about plasma, I'll need some time to do research on it first. Okay, I myself don't know that much about it. Okay, so now we have another little experiment. So can you tell about the shape of the solid cube in each container? Okay, so we have a solid cube, we have a little cube with 3 different containers, but it has to be big enough. Okay, it has to be big enough to fit the cube. And we will be placing the cube from one container to another. So let's try to make a prediction. What do you think would happen to the shape of the solid cube when it's placed from one container to another? Okay, so Steffi said nothing will change. Okay, so many of you guys are saying that nothing will happen. Okay, nothing will happen. But of course, seeing is believing. So let's take a look at this pair of hands conducting this experiment. Okay, so let me play the video back. So solid has a definite shape. So we are using one cube and 3 different containers. This is like FBI, yes. Okay, so we have this hand, okay, putting in the cubes in different containers, like a measuring jug, a bigger measuring jug, okay, and then this is in the basin. This hand belongs to a male teacher, okay. So if you take a look at it, right, you'll notice that as this hand shifts shift the cube from one container to another, it looks exactly the same. Okay, even though the container became bigger, the shape changed. Okay, so what does this tell us? Okay, so what does this tell us? So we know that the shape of the solid remained the same. Yes, it did not change at all. Okay, if it did not change, so this means solid has what does solid have? A definite shape. Yes. Okay, solid have a definite shape. But, okay, so let's continue on to the next one. So we test the shape of a solid. Okay, we test the shape of the solid. Now we're going to test the volume. Okay, now we're going to test the volume. So we're going to use the same cube and we will be pressing the cube against the table. Okay, so let's see what happens. Okay, so let's take a look at our lovely pair of hands and see how he does this experiment. Okay, let us wait for this lovely pair of hands to appear, and it has appeared. Okay, so take a look at this lovely pair of hands. Or lovely hand, one hand, singular. Okay, he pressed it down, he used something to knock on it. Nothing happens. He even flip it to the side and knock on it again. This must be a really bad block for us to keep punishing it. Must be a bad block. Okay, naughty block. So as you notice, while this pair of hands or this beautiful hand did it, nothing changed. Okay, once again, nothing changed. So this means the volume of the cube stayed the same. Okay, the volume of the cube stayed the same. So if we combine the 2 experiments together, okay, we'll know that it has a definite shape and a definite volume. So this means solid cannot be compressed. So since someone asked about clay, clay is a solid. Okay, clay is considered a solid. But how come we can change its shape? How come we can change its shape? It is not being compressed. Okay, it is important to take note that when we say something has a fixed shape or a definite shape, it means it has a shape when nothing is pressing or pushing or pulling it. Okay, so for example, like this Apple Pencil, okay, if I just hold it there in front of me, okay, the shape will not change. Okay, or this packet of chili sauce, okay, the shape will not change if I just leave it there. But if I put in a bit of a push, if the head don't want to be on the chili sauce, if I just put a bit of push, if I push it down, the shape will change. Okay, so although the packet itself is solid, I just add a bit of force. Okay, I just push it down, the shape will change. Okay, but if I just hold it there like this, it has a shape. So this means it has a definite shape. So the shape will change because I am the one pushing it down. I'm putting some strength on it. Okay, so do take note of that. So that's why clay is considered a solid. What about a pencil? We can break it. Yes, but a pencil on its own, right? It has a shape. So it is solid. Unless you're telling me that you put the pencil on the table and it becomes a puddle. If it becomes a puddle, then it will be liquid, or it suddenly loses its shape. Okay. So basically, it has a definite shape as long as we don't do anything to it. So that's a definite shape. Okay. Once we do something to it and the shape changed, then it's fine. It doesn't change its definition. So what about ice? Ice is solid. Yes. Like if you just put an ice cube on the table, right, it does not change its shape. However, it is melting. Okay, it's different. Okay, the shape doesn't change, but it is actually changing in state. The shape, no change, the state is changing. But we'll learn more about that in the future. Okay, when we talk about compress, it means something that is being squeezed. Okay, something is being squeezed to take up a smaller amount of space. Okay, so I don't have anything to show. I don't have anything around me to show compress, but basically if I have this amount of air and then I can compress it so that now that amount of air is taking a smaller amount of space. Okay, so that's an example of compress. Okay, an example is like a sponge. Okay, all of you guys should know what a sponge is. If not, maybe later you can go to the kitchen or go to the sink and press your sponge. Okay, so I can't use a solid or a liquid. I can't use a solid or a liquid because only gas can be compressed. So I can't use like the chili sauce that is on my table or my water bottle. They are solid and liquid. Okay, the sauce is liquid. So I can't really use them. So we'll also talk more about compress in the future as well. Okay, so let's take a look at this work example here. We have diagram Y, okay, showing us a measuring cylinder filled with 120 cm cube or cubic centimeter, depending on how you want to phrase it, of water and stone B in it. Okay, so with the stone, right, the total volume in the measuring cylinder is now 180 cm cube. Okay, so if that's the case, what do we know about stone B? What do we know about stone B? Okay, so some of you guys might be doing math now, 180 minus 120, that is 60. Answer is 60. My math very good. Okay, but do take note, the question says do not mention the volume of P. Okay, so in this case, what we do know is that since we are talking about volume, okay, volume has to do with space. Okay, volume have to do with space. So that means it occupies space. Okay, it occupies space. So someone mentioned that it has mass, it is metal. We are unable to tell. Okay, we are unable to tell. So why not mass? So how come we are not going to talk about mass? How come we didn't say that stone B has mass? Or stone B is a metal? Why are we not saying that? We all know deep in our heart that the stone by the roadside has mass, occupies space, and is considered a metal. But why is it not part of the answer? Why are we depriving the stone of this property? Okay, because it has nothing to do with mass. Close. You have to explain what that it means, Shalin. Okay, the experiment, okay, does not show mass. The experiment does not show anything about mass. The experiment only shows you the volume, and volume is related to space. When we talk about mass, we'll need to use a balance. Okay, we'll need to use a balance. The water level rise, right? Because the stone is occupying that extra space now. It doesn't tell me that. It doesn't tell me how heavy the stone is. Remember, mass, how do we show mass is we use grams and kilograms. So looking at this, right, we don't know how heavy the stone is. So without knowing how heavy is the stone or comparing with another object, we can't tell the mass. So rising level is occupied space. It's pushing the water away. So basically, if I go back to the earlier slides, right, we will only know about mass. Okay, we can only determine or compare mass if we are using an instrument related to mass. Okay, only if we are using an instrument related to mass, like a beam balance or an electronic balance. So if we are not using any balance in the experiment, right, we cannot prove that the object has mass. Okay, although we know deep down, yes, it has mass, but the experiment does not show it has mass. Okay, hopefully those who are confused have a better understanding now. So you have to take note what is used in the experiment so that you know what they are asking for. So measuring cylinder, it measures volume. Okay, so volume, space. Finally, we are going to talk about the bubble question. Okay, finally, we are going to look at the bubble questions. Okay, remember what is shown in this experiment, okay, or what is shown by this action. Okay, so as you guys can see, the answer is 3. Okay, the answer is 3. Now, why is it 3? Okay, why is it 3? Same thing as the previous work example. Is there any balance in the question or in the experiment? There is no balance. Okay, we only know that he's trying to squeeze 10 books into the box. So if that's the case, we don't know if the books have mass. It could be a space book. Okay, a book that doesn't have any mass at all. We don't know. Okay, but we do know it has definite volume because it occupies space. It has a definite shape because we cannot, if you take a look at all the books, they are all the same shape. They are not being squished or anything. Okay, if they do not have a definite shape, maybe we can still try to squish it, or like fold it in a certain way so that you can make use of the additional space or the unused space. Now, based on the experiment above, okay, now it's another work example. Based on this work example, what do we know about the two properties of the objects, of object A, object B, and object C? Okay, so once again, what are we using? We are using a measuring cylinder, okay, or a container of water. So if we are using a container of water, we will be looking for space and volume. Okay, if you are using a container of water, okay, we will be looking at the volume. Any container of water. But if you want to measure, then we need to use like a measuring cylinder. Okay, so as long as we have a container of water, we are testing volume. So for this one, what do you think will happen when the block goes in? What do you think will happen when we put the block in to the displacement can? So based on the past few experiments, right, we know, or based on the past few questions, we know that when this goes in, the water level will go up. The water level will rise. But what happens when the water level rises? Will it still stay in the displacement can? It will not stay in the displacement can, but it will come out into the glass. Okay, so this is actually a form of experiment used to test for something, but we'll talk about that in a later lesson. But since the block forced the water to go up, once again, water must be volume and space. Okay, once again, it will be volume and space. What is the string for? To hold the block above the can. Okay, so now we have another video. Okay, and this person seems to be wearing a pretty interesting shirt. Okay, water has no definite shape. Let's take a look at how this experiment proves that water has no definite shape. Okay, apparently a cat is going to be showing this experiment. Okay, so this cat shirt wearing person is pouring container or water from container A to container B to container C. Okay, and if you notice, the shape is changing. Okay, the shape is changing. So as you can see, from container A, the shape is different from container B. Okay, the water actually takes the shape of the container. Now it's a cup shape, circular. And then when we pour into the square container, it is now square. Okay, so thank goodness it didn't become like what the shirt is portraying, and then there was like some smoke coming out from the water or from the liquid. No, okay, maybe I'm not that mad. So this means that liquid does not have a definite shape. Okay, it might be, it shouldn't be losing volume. Okay, Xavier, because if you're pouring carefully, right? If you're pouring carefully, you should not be losing volume as long as all the water is transferred. As long as all the water is transferred. That's the thing you have to take note of. Okay, if that's the case, what does it mean when water from the bottle become round and then become circular? So it becomes square. So this means it does not, it takes the shape of the container. It actually follows the container. So if you pour from one container to another container, the shape of the water will change. So this means it has no definite shape. Okay, the shape is not fixed. It will always follow its container. Just like when you pour water from, let's say, the water boiler into your cup, the shape definitely changed. Okay. Okay, and then we have another experiment. And this time we have more than one hand or more than one pair of hands. Okay, so this one will show that water has a definite volume. So as you can see, this hand is showing us a syringe with blue colored water inside. And it's calling someone to come and help him. So this someone helped to push. Okay, after pushing for a long time that we actually need a video, that we actually need a transition, you'll notice that the volume did not change. Okay, okay. So this shows that no matter how much you try to push the plunger in, right? No matter how much you try to push the plunger in, water do not get compressed. Okay, water do not get compressed. So this means that it has a definite volume and it cannot be compressed. Okay, because you can try that at home as well. If you have a syringe, just put some water inside, just keep pushing and pushing and pushing. You will notice that it cannot be compressed. But please do not push hard enough that you make a hole from your other hand. Okay, push it hard enough that you start to feel pain, but don't push it so hard that it starts bleeding. Okay, anything pushed hard enough can injure you, even if it's not that sharp. Okay, so with the last few minutes, let's try to blaze through the last few bubble questions. Okay, so which of the following statement is not true? Not true. Okay, 1 minute starts now. Okay, so I will not be going through this question because it was immediate. It was based on the previous slide only. Okay. Okay. So as we have shown in the previous video, water cannot be compressed. Okay. This is can, but it's supposed to be not. Okay. Question 3. Okay. The answer is 3. As you pour the water in from one container to another, it will follow the shape of the container. Okay, even the water level will change because it can only occupy that much space. Okay, so one more question. Okay, so the answer is A only. It is only A. So once again, this is not shown in the action. Okay, if you keep adding water, right, we don't know whether does it have a definite volume. Definite volume, and you have to test by whether or not it can be compressed. Okay, by adding water into a balloon until it bursts, it is not testing if it can compress. And we have no idea what is the shape of the balloon. Okay, this is not shown. So the only thing we know that is taking up space until it actually causes the balloon to burst. Okay, bye-bye.